So thanks for joining me to listen my lecture regarding the harmonic waves. So essentially I will be generalizing the notion of plane waves here so that we could really qualitatively and even quantitatively understand propagation of fields in more complicated settings. So for example, we could understand how a free space interferometer works, for example, Mach-Zehnder interferometer or Michelson interferometer. And there, once we understand how such instrumentation can work, how a superposition field would be calculating inside such kind of instrumentation, we can, in the follow-up chapter 8, really understand better all the needed things regarding interference effects. So this is my brief motivation to this lecture. So I will be generalizing the notion of plane waves. I will be doing the math, how we can calculate superposition waves. And essentially there, as a spoiler alert, I would say that it's really the relative phases of the two different fields that matter. And then I will form an irradiance pattern. So what kind of interference pattern emerges when we are summing two waves together, and then how that looks like, essentially. So this is what I will be speaking here in this lecture, and I will now start my journey. So we have mentioned earlier that it's really the superposition of two waves that is of interest here, and really the superposition depends on the mutual phase difference of these two fields. So it's really the phase arguments that are of key here. The argument inside the sign, if you are using a sinusoidal representation of a field, a plane wave, or the argument inside the exponential function. So that's the key relevant quantity here. And let's start by just considering how two fields can be summed. And let's use the notation based on the complex numbers. And let's start, as always, with a time harmonic plane wave. And now it's propagating along the z direction. So essentially, we are dealing with a quickly oscillating field. That's why I have the tilde there, representing the fact that now I have essentially a rapidly oscillating field with respect to time variable. So in the future, I will be introducing to you the Fourier transforms. So essentially, in that kind of context, the tilde here would mean that I'm having my function E now described in the time domain. So that I haven't Fourier transformed that field distribution into the frequency domain. And in the same kind of slang, I'm saying that it's a rapidly oscillating field. So I can divide this field into two different kind of terms. I can describe the propagation, so basically the harmonic plane wave contribution, and then I can describe the time oscillation using this simple time harmonic function, exponent I omega t. And now I can break the position dependent part, so the propagation point part, the harmonic plane wave part, into a term where I have the amplitude of the field A times some kind of initial phase, exponent epsilon, and then I have my time-dependent harmonic plane wave contribution propagating in the z direction, so exponent I kz minus omega t. So this is my field, and I will now basically sum two different kinds of fields with slightly different initial phases together, and let's see what we get out. So here the E tilde notation just means that this field oscillates rapidly with respect to time, and the EZ is essentially this plane wave contribution. So we have A and the initial phase E exponent I epsilon here, and then I have my plane wave contribution. So it's just for simplicity, we're only considering a propagation along the z direction, but of course we could equally well just use a propagation into an arbitrary direction, and then we would have the wave vector here with a dot product of the position vector r. But for simplicity, this is equally fine. We can always just simplify our treatment by just assuming that we're propagating solely only in the z direction. Or we generalize the concept of the z direction, and that also works out. So the field is propagating along the z axis, and let's now generalize the treatment so that we can consider fields propagating in a more arbitrary way, and not necessarily even in a straight path, but it could also be just a propagation of a field inside a fiber that can be, for example, turned into a coil and be bent and so forth. And let's look what is the simplest way how we can describe things mathematically, that we could still use it to describe more arbitrary looking paths where the light is propagating. So for example, we can imagine how a light is being propagating inside a fiber, optical fiber, so it's going to find there, and then we can even bend the fiber into different kind of twists and turns and coils, and still light is being propagating there. And essentially we do not need to consider that complicated piece of math. We just only need to generalize the concept of z, the propagation distance, so that it would actually be the path traversed by light inside the fiber. So instead of just using like a simple Cartesian coordinates, we can generalize the notion of z propagation direction. So we can do this generalization by just thinking of a line integral formulation of a optical path length, OPL. So as we defined earlier, the OPL, the optical path length, we were able to essentially just form that as a summation of different kind of propagation lengths. So Ni was the refractive index associated with the kind of short discrete propagation through a medium of interest, and S would be the thickness of this medium propagating. And then we can generalize this discrete summation into a line integral. So we are now integrating a kind of arbitrary line, S, so it can also be curved. It doesn't need to be a straight line anymore. And the only thing we must consider here is that we are actually integrating the refractive index profile through this line, so that we are performing that kind of line integral. And that gives me essentially a kind of parameter that mathematically in the plane wave notation we just used in the previous slide, I can just use this as my z, and then essentially this z is a generalized variable. So that graphically, I will try my best to show here what I'm saying here. I can, for example, try to understand how a path, how a ray of light would be propagating through a lens that has a refractive index of n. So that now I can think in the discrete case that I'm just propagating light through a straight path. So I'm starting from this point, and then I'm propagating a distance into here. So essentially to the interface between the air and lens, and the distance of propagation is S1, and the refractive index here would be the Ni. Then I'm traversing through the lens, and I'm a distance of S2, and now the refractive index profile here would be the N, or just denoted N2 here to comply better with this summation formula used here. And then finally, I can think that my final trace of a ray would be into this point, and now in a refractive index profile of N3, and the distance would be S3. So here, this is essentially how I could understand things. I could calculate the optical path length OPL by just using a discrete summation like this. If I'm decomposing my propagation into these three different lengths of optical path distance. And now, of course, I can generalize this treatment, and I could really consider a curved path. Of course, like if this would be a air and lens here with a constant refractive index profiles, light wouldn't really be propagating in this kind of very curved trajectory. But at least I hope this graphically makes sense. That how do we generalize our z variable to be a more arbitrary path the light is propagating. So now, instead of like thinking as a discrete summation, I'm actually trying to integrate through the line denoted with S, and I want to know what is the phase accumulation of my field when it's propagating from this point into this point. And essentially, all I need to know is that I will need to calculate like the line integral of refractive index profile as a function of S, and then of course I'm multiplying that with the differential length of my line, so ds. So this would give me the propagation of the field from point A to point B in a more arbitrary setting. And this is essentially what we will be using in the future. So this is a so-called generalized notation, and it really allows us to describe a quite arbitrary propagation paths of a field. And simply, we can still write the propagation in terms of mathematics, that we would have the field, now in this given position of interest Z, where the Z should now be understood as a generalized coordinate. So it doesn't have to be exactly on a kind of Z axis, but rather like it could be rather like a point S. But we only need to understand how light is being propagating along a curved path. And this is now simply A times exponent IA alpha, where alpha is now essentially the initial phase epsilon plus the propagation due to a distance of Z, where Z is now, of course, the generally speaking, the generalized coordinate. So let's now take two of these kind of fields and let them interfere. So let's consider a superposition of two fields that are oscillating at the frequency omega. And we want to keep the treatment as general as possible. So let's assume that we can have two different kind of initial phases, so epsilon 1 and epsilon 2, and the paths Z1 and Z2 that the two different fields are traversing are different. So essentially, mathematically put, we assume that epsilon 1 is different from epsilon 2 and Z1 is different from Z2. And let's now calculate the fields. So essentially the fields, the time-dependent fields can be written that they are time harmonic waves, and the first field E1 depends on the Z1 coordinate, and it oscillates harmonically with respect to time. So we have this exponent I omega t phase relation there. And then the E2 field is of a similar form that now depends on the Z2 coordinate. So that the position-dependent terms, of course, are of a form that we have some kind of initial amplitude, and then we have initial phase, and then we have the propagation into the point Z1. And then this can be written that it's just the complex valued A1. So we hide the initial phase into here. Sorry, we don't. So that we just I'm confusing myself with this notation. I'm just having sorry, yes, the kz dependence was inside the alpha parameter, so alpha was defined that it was the epsilon plus kz. And now the second position dependent term, the E2, it's of a similar form, and that can be also very simply written that it's the amplitude A2 times the phase term exponent I alpha 2. So that the phase terms, alphas, they include both the initial phase, EIs, and the phase caused by the propagation of the wave. So essentially this kz term here, and let's remember that the z can be in a more arbitrary looking propagation. So it doesn't need to be a straight path, but we can also consider a propagation of field inside a waveguide that is bent and curved, or it could be a fiber, or it could be other kind of complicated things. So this is what we are dealing with. And even in a complex setting, we can still sum very simple looking fields together, and this kind of summation we can already do. Nothing complicated about that. So the superposition of these waves, we can really easily calculate that. I do not go in details with the mathematics, so I'm basically just mathematically summing things over. I can first take the time dependence to be a common term, so the exponent I omega t can be taken out, and then I insert what kind of fields I had. So this was the kind of more general way of describing things, or a more easy way of describing things. And now I'm just taking, for example, this exponent I alpha as a common term so that I can more easily calculate a phase difference. So I'm multiplying both sides, or I'm taking this out, and then I must multiply this term so that I can take the term out. So essentially I can have this kind of multiplier inside the parentheses. So I have A1 plus A2 times exponent I A2 minus A1. And now I'm multiplying this with the exponent I alpha 1, and I have the usual time dependence. And now I can really calculate the superposition irradiance or the irradiance distribution of this superposition quite easily. Since these two terms, they are exponents, and I know that the modular square of these guys gives me a unity. So only thing that is left that gives me of some kind of interference effect is this term. And I only need to look into that. So then I can calculate the irradiance, and that would be the proportional to the modular square of the total superimposed field. And now I can just simply calculate this using the terms inside the brackets, and then I'm calculating or basically I'm multiplying that with the modulus. Sorry, not modulus, but the conjugate of this term. So then I have my A1, it's a real valued quantity, plus A2 times, and now I have the phase term, so I must conjugate that. So I have exponent minus I alpha minus A1 there inside the exponent. So this is how I'm calculating the modulo square, and this can be easily progressed. So what is left? So on the left hand side, the first terms are the moduli of the amplitudes, and since they are revalued, I do not even need to use the absolute notions here. So I have this kind of distributions, and essentially these would be the irradiances, or these would be associated with the irradiances of the individual waves, and then I will have some kind of interference term. So these, we would have whenever we would have just individual waves. So if we would, for example, have just the wave 1, I would have irradiance that is proportional to this term, and if I would only have the wave 2, I would have an irradiance distribution proportional to this one. And then when I'm superimposing these two different fields, then I also have this interference term. So I have 2 times A1 times A2 times cosine of alpha 2 minus alpha 1. And this is the interference term. And looking at it, it essentially depends what we have inside the cosine, what kind of values it can have. So ranging from 1 into -1, and there it's really the phase difference delta defined as the alpha 2 minus alpha 1 that defines, do we have larger irradiance when we are superimposing fields, or do we actually have a reduced irradiance? So do we have a constructive interference or destructive interference? And now let's look at the phase difference, so that the delta term, it's given by alpha 2 minus alpha 1. So we can insert what kind of forms we have for the alphas. So essentially what we have is that then we have the difference between the initial phases, so epsilon 2 minus epsilon 1, and then we have so this is the difference between the initial phases, and then we have a term arising from the propagation of fields. So basically the wave number amplitude k times the difference between the generalized propagation coordinates. So z2 minus z1. So this would be my optical path difference. And waves are periodic. So in principle, we would have infinitely many minima and maxima. So if we just would look into different kind of propagation, we would have many different minima and maximas. So here we could look into the maximas of the irradiance distribution as a function of propagation direction z. So essentially we get maximas when the phase difference is a multiple of 2 pi. So m here is an integer. And we have minimas of the irradiance. So it's essentially destructive interference when the phase difference is a 2 pi m plus pi. So essentially a pi multiple. And here the irradiance of the superposition wave is essentially as recalled. It's given by alpha 1 squared plus alpha 2 squared plus this 2 times A1 times A2 times the cosine of the phase differences. Alpha 1 minus alpha 2. Alpha 2 minus alpha 1. So now this is what gives me the irradiance pattern, and this will be used quite a bit in the upcoming chapter regarding interference. And please remember here always that even though this seems that we are only considering propagation along a very specific direction, we are now speaking of a generalized quantity. So this same math could be also used to understand superposition for fields in a more complex and arbitrary settings. So we could, for example, form a superposition of fields taking place inside a waveguide interferometer, or a interferometer done using fibers, and not just in free space settings. So this is my main take here with this slide and the upcoming slides. And let's now finally generalize our treatment into a superposition of n waves. And here we can just easily calculate that to be, and I do not do the math, but I will just show it so that we have a superposition of waves. So we are summing through all of these waves that we are considering, all n number of them. So essentially I'm summing all different time harmonic waves, and for simplicity, since I'm assuming now that we have same frequency for each waves, I can take the time harmonic contribution out from the summation. So what I have left is a summation of the position dependent terms, and what that is essentially it's the AJs of exponent I alphas is still time harmonic contributions. And this I can actually simplify this summation here. I can always write this kind of sum as a single position dependent term. So I can just write that this summation is always of a form that I have some amplitude A times phase term exponent I alpha times the time harmonic contribution exponent minus omega t. So this is what we have now basically always when we are just summing n2 waves. And this is the case that we really see that mathematically, and if it's mathematically the case, also physically, this would be the reality. So when we are summing n waves, we are really seeing that the superposition wave looks like a single wave. And how come this is the case is that essentially we are really assuming here that we have perfect coherence in our system. So this is what we are implicitly assuming here when we are doing our treatment. But if you ever need to generalize the treatment to a more realistic scenario, please note that this is where the magic happens. So we are assuming that these n waves we are summing together, they are perfectly coherent. And then when they are perfectly coherent, the mathematical outcome is that we can understand that the propagating field, the superimposed field, as a single plane wave propagating through space. But the second we start losing coherence, so that not the different waves anymore are perfectly coherent, then something else would actually start emerging for here. So there would be actually some kind of a stochastic nature present, and then we should really need the mathematics, change the mathematics accordingly. But we do not go into that kind of generalization of the math here. So we should really start using a stochastic treatment of electrodynamics. So instead of a single plane wave, we should actually look into the distribution of plane waves, and we should have some kind of randomized or semi-randomized phase arguments here, and the math quickly would go into a quite more complicated. So we do not do that in the introductory course because we don't really need that to understand the very basics. But if ever you need to go there, now you have been warned or noted that the coherence properties of light distributions are really the key here. So this was my lecture of now. I have been speaking about the harmonic waves. And in the next lecture, I will be looking into standing waves. So essentially, I will look into a different kind of superposition of waves. But more on that in the next lecture. So thanks and bye-bye.